Yeah, I am Avishay Yanai, and I'll speak about the gcEVM, which is a garbled circuit extension to Ethereum virtual machine. So this talk deals with the problem that we have in blockchains currently, which is that everything is public. And once you give your key to someone, it can track your activity from that point and forever. And it's a very large problem for the adoption of blockchains, which gives us a very good benefit for fast transfers worldwide and cheap transfers. But we cannot really use it because consider a business that wants to bring its operation on chain, then everything becomes just public. All payments to service providers, employees, and actually everything. This simply cannot be public to everyone. Other applications are related to ownership structures of companies on some products, intellectual properties, and so on, governance, elections, and polls, making DeFi more fair. And we know the problems of that MEV brings to this space. We can deal with seal build auctions, and of course also with partial information games that requires privacy. So all of these are applications that in order to run them on chain, we must have some privacy preserving solutions for smart contracts. So what is the gcEVM? The gcEVM is an MPC-backed EVM extension that simply adds more instructions to the EVM. So the EVM comes with a specific instruction set, and we add additional instruction sets that when you trigger those new opcodes, they will, when you call those opcodes, they will trigger an MPC operation in the backend. So an additional feature of this system is that it adds on-chain randomness. So whenever you need randomness, for example, for games like poker or mastermind, then you will be able to get it instantly. So how users and developers interact with that system? So in the gcEVM, each user has a symmetric key encryption that is associated with it. And when a user comes and wants to send secret information to the gcEVM, it needs to first encrypt it using its secret key. And this means that when a new user comes to the system, it needs to onboard and ask the system to generate an encryption key for it, a symmetric key encryption key for it. And from that point, it will use that symmetric key in order to encrypt information to the system. And so, as I mentioned, the MPC nodes will store secret shares of the keys for each user. So, if I'm an MPC node, I will have a key share for each user, as well as another key share for the network, which we call a global network key. So we use the user's key in order to do encryption and decryption specific to the user. But the global network key, we use it in order to store information for inside a contract state if we need to use that state in later stage. I'll show you the flow in a bit. Finally, developers, if they just migrate their smart contract directly from Ethereum to the gcEVM, it will work just fine because it's the same VM underneath, but it still will not have privacy. It's not automatic. To have privacy, the developers need to adjust their smart contracts a little. So, for example, if they want to preserve privacy for an edition, they will need to change from simple edition to our secure edition. So if we look at the execution layer, then we distinguish between three types of encryptions. So we call it input text, garbled text, and ciphertext. So ciphertext is the thing that we all know what it is, just the result of the application of encryption on some plain text. But there are two other types of ciphertext that we want to consider. One of them is input text. This allows users to input new information to the system. And garbled text is a form of encryption that allows us to do some operations on the ciphertext. So the overall flow will be as follows. So users will send transactions to the gcEVM execution layer, and those transactions will include both input text and plain text. So the idea of input text is that they contain a ciphertext as well as a signature on the metadata of the ciphertext. And metadata contains the address of the sender as well as the destination of that ciphertext, which is the contract address as well as the specific method that the user wanted to call. And we add this signature on this metadata because we wanted to make sure nobody will steal the user ciphertext. It's not like a two-party system where the trans over TLS that I can encrypt and nobody actually can intervene in the middle. Here, all ciphertext will be online, and therefore we need to make sure nobody who sees my ciphertext will be able to later use them, or either on my behalf or as part of other users' ciphertext. So this is the idea of input text. So when a transaction arrives to the execution layer, it has inside it some input text and plain text. And the input text are first going to a validation phase where the signature is being validated, and also it validates that this is the right contract and method that the user wanted to call and not something else. And if it passes the validation, it goes into the garbled execution environment where everything there is in the form of garbled text. And this allows us to do operations on secret information using garbled circuits. And after we are done with the computation, the output will be in the form of a garbled text as well. Then it depends on whether we need to give some ciphertext back to the user or store some ciphertext on the contract. If we need to do something like that, then we'll take that garbled text and do encryption on it to the right key, either to the user or the contract or to both. And this will gives us ciphertext, and it will go either on a receipt to the user or be stored in the contract state. So this is the overall flow of the execution layer. Just as an example, this is the confidential ERC20 contract, actually just the transfer function. And you can see in the first box here, we have two variables. This is a CTUIN64, which represents the amount that the user wanted to transfer. And the signature, which is what I mentioned, is part of the input text. So together, those two variables are called IT for input text, and they're going into validation function. The MPC core validates ciphertext. This function validates that the user actually wanted to call the transfer function on this confidential ERC20 contract, and this is actually the message sender. It's signed by the message sender. So this is the first step when we enter new information to the execution layer. Then later we call to if it validates, then it goes into a contract transfer function, which takes the resulted garbled text and changes the balances of the sender and receiver according to the amount. And the result will be stored in the garbled text as well, which is called GTBool, the variable called result. And this variable is also secret. And whether we open it or not depends on the user intention. If the user decided by giving us reveal result true, then if it decides to open the result to everyone, then we'll run a decryption on the result, basically just using the decoding information of the garbled text to show everyone that the result was successful or not. This is how the entire network looks like. So when after users send transactions to the network, they first get into a sequencing subnetwork. These are just simple nodes. Everything, by the way, runs on fork of Go Ethereum. So when transactions arrive to the network, they first get into a sequencing subnetwork, and the sequencing subnetwork just generate something we call red blocks or non-canonical blocks. These are blocks that represent just blocks of transactions that are not executed yet. It means that it needs to get to a second phase of execution, where those red blocks become black blocks, which means they are canonical block or blocks after execution that actually changes the state of the chain. And the reason we separate both sequencing and execution is actually inherent to all MPC-based networks. And the reason is that sequencers cannot make blocks final. And this is because if they try to make blocks final, it means that when they validate a transaction, they need to actually execute it. And in order to execute it, if it has some secret information in it, they need to call an MPC. And if they call an MPC and the transaction requires to decrypt some value, and then this decryption might leak information about some user or some state of a contract, and they simply cannot reveal that information because the transaction is not final. So it's like a chicken and egg problem that we solve, at least in our case, we solve by separating sequencing and execution. Here, we first sequence transactions into blocks. We don't execute them. Then those blocks of just ordered transactions are getting into the execution layer after they are kind of sealed in initial phases of sealing. And only in the execution, we can run the MPC on transactions that have secret information in them. So here in the execution layer, we have, as you can see, two types of machines. We have in the lower layer the garblers, and in the upper layer the MPC evaluators. And I will talk about it a little bit in a bit. So I would say that most of the audience know what Garbled Circuits is, but I'll just make a brief intro to it. So consider, so as you know, in MPC and in FHE, for example, then we present functions as circuits. Then we do the same here with Garbled Circuits. Consider an AND gate that has two input wires, A and B, and one output wire. Then the gate will look like this. So all combinations of bits on A and B will take us to 0, except in the case where A and B equal 1. When we translate it into a garbled gate of the AND gate, then we have that the garbler generates two possible keys for each input wire. So for A, it will have A0 and A1, and they just encryption keys, so they look random. And A0 will represent the value 0, and A1 represents the value 1. And the goal is that when we give one of the keys on each input wire to the evaluator, as well as something called garbled gate, the evaluator will be able to obtain the correct key for the output wire under the same functionality as an AND gate. So, for example, if it has A0 and B0, it will be able to obtain C0 in the end. If it has A1 and B1, it will be able to obtain C1 in the end. So the idea is the simple YAO-based protocol where we encrypt each of the output labels by all combinations of input, keys, not labels, by all possible keys of the input wires that lead us to that specific key. So we will encrypt C0 using the keys combination of A0 B0, A0 B1, and A1 B0. These are the three first rows in the table there. And finally, we'll encrypt C1 using the combination of A1 B1. Now, there are two privacy or security guarantees that we need to satisfy when we do garbled circuits. One of them is that all the labels or keys actually they look random to the evaluator, and this means that I also mentioned this. This is only for illustration. It's not really secure. In order to make it secure, we need to somehow permute the rows in the AND gate. And so we need the evaluator to not know which keys actually he's got. So he doesn't need to know whether the keys that he's got represent 0 or 1, unless he's the one who inputs them. And authenticity means that the evaluator will not be able to obtain the different output key. For example, it will not be able to obtain C0 if the actual result that it needs to obtain is C1. So this is the authenticity. In two-party computation, we use garbled circuit by having the garbled function and sends to the evaluator the following. It will send the evaluator the function, the garbled gate, after doing the garbling and generating a table like I showed you before. And for each input of the garbler will send the right keys. So here the garbler knows the keys for A and B, but not the correct key for wire X. This is a special gate called OLE on bits. It doesn't really matter what it does. To obtain the correct key for X, the evaluator will need to run the oblivious transfer subprotocol. And then after it got the three keys, it can evaluate the garbled circuit on those keys and use the decode information in order to translate from the key on the output to the actual value that it represents. So this is the very high-level overview on how 2PC with garbled circuit works. Now, for gcEVM, when we want to extend it to multiple parties, we could go with the approach of multi-party garbling that has many works in the literature. But the problem that we were tackled there is that in all of them, the computation as well as the garbled circuit size, it increases with the number of parties. And at some point, it becomes not very efficient. And what we wanted to maximize here is the runtime online. So whenever we got some computation, when we got a block of transactions, we want to be able to run it as fast as possible. So, so the approach we took here is that we can go with the two-party case that I mentioned before and separate the roles of the garbler and the evaluator and distribute each one of them separately. So we'll have a bunch of garblers, and actually in practice it will be a bunch of committees of garblers and also a bunch of evaluators. Each one of those groups will have different threat models. This is actually gives us the flexibility to have different threat models on these two groups. And the idea is that garblers will work continuously on generating garbled circuits, spit them out to the group of evaluators, and the evaluators will store a database of garbled circuits they got offline from the garblers. And only in real time, when we got some block of transactions that require to compute transactions with privacy, they will consume those garbled circuits and run those transactions. So yeah, so the idea is based on the following on the following feature, which is called soldering, that we can apply to garbled circuits. So soldering allows us to take several garbled circuits and stitch them together into one garbled circuit that does a bigger functionality, for example. So this idea is being used by our solution by having the garbler generates many garbled circuits for each opcode of the EVM. And the garbler doesn't need to know anything about how those garbled circuits will be used. So the garbler works in completely offline manner. And only in the online phase, or actually in real-time computation, when we know what we want to do, what is the function that we actually want to compute, the evaluators, they will take a bunch of garbled circuits, depending on the function, and they will stitch them together in order to represent the actual function. So, for example, if the function is transfer, as I mentioned before, then that function will be represented by smaller garbled circuits. Each is doing one simple operation. So, for example, greater than or equal, or addition and subtraction, and finally MUX on whether the transaction was successful or not. There are two types of soldering that we can do. One type of soldering is called online soldering. It means that, for example, if you take the result of the GTE gate or GTE gadget, then only when you get the key on the output of that gadget, you will do the soldering with the MUX gate, MUX gadget for specifically. And this is online soldering. It means that only after having a key on an output wire, I will solder it with the next wire. Online soldering is working, but it will take us some communication rounds to do those soldering, and we don't want to spend communication rounds in online. This was the whole point of going to of actually using garbling. So the idea is to use something called offline garbling, and all those arrows that you see, the blue arrows that connect gadgets together, we can actually do the soldering all in offline. We don't need to know what is the active key of the execution. We can already connect wires one another in an offline phase before we know the computation result. And this will save us a lot of communication rounds in the online phase, because we can do something called pre-execution on the block and see which gadgets should be connected to which other gadgets, and connect all gadgets at the same time before we actually run the block. Final feature that we can achieve using the garbled circuit approach is public verifiability, which is a way to ensure that the computation was done correctly, even without participating in the protocol itself. So even if I'm external party, we just see what the MPC parties are doing, I will be able to check that they are doing it correctly. And this is important in blockchains because we want to make sure that nobody steals our funds. This is a basic feature that we want. And we can achieve this using garbling by adding some additional material to the garbled circuits. And specifically, we add homomorphic commitments on the permutation bits that will later allow verifiers to re-execute the entire circuits the entire garbled circuits, and also make sure that the soldering was done correctly. So the gcEVM is first deployed on Kotlin network, and it has several features. Right now, we are running with one garbler inside the TEE and many evaluators. The number of evaluators is very flexible, and their threshold is also a parameter. We are using AES 128-bit encryption in counter mode. And for onboarding users, we use key encapsulation mechanism of RSA. We are managing about 50 confidential ERC20 transfers per second. This is the same contract that I showed you before. And this is without the offline soldering. With offline soldering, we are expecting to have about 1,000 transactions per second, simply because we save all those communication rounds in the middle of the execution. And it runs on very normal machines. The bandwidth per ERC20 transaction is about 1 megabyte. Most of it is taken for the AES circuits. But we are trying to reduce the number of AES circuits that we use. And after we do this, we can reduce that number by a factor of 5. So I described before only a layer 1 solution, but we realized that we can take it beyond layer 1 into something called the rollup. So the premise of a rollup is that everything is secure by the base layer. Most of the rollups are working on Ethereum. So the goal is to have the same Ethereum security, but using a different network that does batches of transactions and make everything cheaper. And we understood that we can combine the interactive fraud proofs of Arbitrum with garbled circuits in a way that I will not get into much details here, but if you know the Arbitrum's protocol, then there is a bisection protocol where a tester and the guy who gives a dispute, they need to decide who is right and who is wrong. And this has to be this decision has to be taken on the contract on Ethereum. And the Arbitrum's idea was that the decision of who is right and who is wrong will be very cheap if the contract has to run only one opcode. And the process of finding which opcode it needs to run is called the bisection protocol. And we realized that we can do the same bisection protocol on garbled circuits, so that the contract on Ethereum will need only to know or to actually re-execute one garbled gate, which is one AES computation. So I will not have time to talk about it too much. And with that, I will finish. Thank you.
Floor is open for questions.
Hey, thanks for a very interesting talk. So if I understand correctly, then the MPC evaluators are consuming garbled circuits, so you have communication complexity. And then you're executing the evaluator using secret sharing base, so you also have route complexity. So you are just taking like the worst of the two.
So we have secret sharing on all the keys. So for example, in two parties, the evaluator gets the correct key on a wire by running a oblivious transfer. And in our case, the garblers will both publish the garbled circuits, as well as give secret sharing on each on each key of a wire. So they will do secret chain on both keys, both for the 0 key and the 1 key. And only in real time, the correct key will be revealed to everyone. So that phase is actually replacing the oblivious transfer, and it takes us right now 3 rounds of communication. And right now we are doing online soldering, but when we do offline soldering, then all these 3 rounds of communication can be used for the opening of all keys for the entire big circuit, for all small gadgets that we combine together. So overall, at least theoretically, we can spend 3 rounds of communication for the entire block, and then everything will be run locally.
Okay, so you also have like constant route property in the evaluation phase. Okay, thanks.
Yeah.
I have a second question. So because like you are using the public verifiable transcript technique for making the execution verifiable, right?
Sorry, I didn't get it.
So you commit to the labels for using homomorphic encryption commitment scheme like maybe Patterson, so that the verifiers can re-execute everything, like don't know the actual input, but still knowing that the circuit is executed correctly. But like because like it is group operation, so it is very, very costly. You know, like I think. So
yeah.
What is the? Do you know what is the cost?
So you refer to the public verifiability. Right?
Yeah.
Yeah. So for public verifiability, we don't need to commit to all labels or to any label. Actually, we need to commit only to the permutation bits. And the idea of that homomorphic commitment is to only make sure that when we do soldering, we actually the evaluators, when they do soldering, they will later be able to prove to everyone that the soldering was done correctly. So they don't connect a key that represents 0 with a key that represents 1. This will actually enable them to cheat. And for this, we only do homomorphic commitment on single bits. And it's like, if you want to re-execute everything, you don't need to do a lot of group operations. It's very, very minimal.
Okay, thank you.
Hi, thanks for your talk. So is it accurate to say that for each execution, we would need to consume a bunch of garblings?
Yes.
Oh, I see. So I'm just curious, like, what's the performance like? So the garblers need to be constantly just producing garblings for every possible opcode, and the evaluators need to be obtaining like the outputs for all possible like outcomes.
Correct.
opcode.
So Garbler has to produce garbled circuits for every possible opcode, and this is actually better than the need to generate a garbled circuit for every possible contract function, right? So this would be very wasteful. Currently, the Garbler, we wanted to make it like extremely secure, and it's inside the TE, so that nobody need to actually talk to that Garbler. It only spits information to the public. So no ingress information is coming to that machine. So the Garbler is not even aware of which garbled circuits were consumed or not. This will, and so it might generate garbled circuits that will just go to the trash bin. They will never be used, and there is no database to even hold them. Just because maybe generates a lot of division circuits that are not used that frequently. But we are planning on having the Garbler more aware on what will happen on chain and adjust the rate it generates garbled circuit on each opcode. So it will be less wasteful.
Thank you.
Excuse me. Hi. Yeah. Hi. Yeah. Interesting talk. Very nice idea. I think one limitation I can see is the bandwidth. So just in like a transfer is taking up like 1 MB, right?
Yeah. So the highest bandwidth, like the bandwidth is mainly because of encryption decryption subcircuits. Right now we use AES, which are quite expensive. There are many, several ways to actually decrease the bandwidth. One of them is to use a different PRF that is more efficient. Another would be to make the evaluators stateful. So right now the transfer, it needs to perform 5 encryption and decryption garbled circuits to evaluate them. And we can reduce it to only 1 if we allow evaluators to be stateful and store garbled text instead of ciphertext, basically. This is also connected to the first slide. This is just a simple idea that allows us to decrease the bandwidth about 5x. And we'll think about more ways to improve this. One of them would be to use more efficient garbling schemes that allows us to do some arithmetic operations on instead of only Boolean operations.
Yeah, following up on that. So let's say 10 years down the line, 5 years down the line, there's some like advances, more efficient protocols. So how do you plan on updating those in a live blockchain?
I didn't get the question, but I'll be happy to talk to you offline.
Okay.
Because thank you.